Yesterday we have discussed two level of modeling that are data flow and gate level. So we have just introduced our next level, that is behavioral modeling. So we will be discussing more about behavioral modeling and how to design sequential circuits and combinational circuits using behavioral modeling. Before going into that, I need to discuss a little bit concept of data flow modeling and gate level modeling. So when we are designing a large circuit, means when we have a large architecture, there will be so many modules inside that large architecture. For example, if you are designing a processor, there will be memory element will be there, controller element will be there, sequencer element will be there, then ALU element will be there. So these all modules are submodules of this large circuit. So we will be designing each submodule if we are working under a team. And for example, in my team there is five members. Okay, so if I have five submodules, I will be dividing each module into my group members, and they will be designing that. And we can club all this code, and we can create a top module. So how we will create that kind of design, I'm going to discuss first. So I need to design a full ladder using half adder. So for that we need a half adder module. Then we need to include that half adder module into our full adder design. So everyone know how many half adder and half adder is required to design full adder. So I'm going to start here module half adder. Then we have input say comma b and some comma c carry. Now inputs are a comma b and s and c. Okay, so I'm using here data flow modeling. S is equal to a XOR b and okay. So we have designed half adder module. Hmm. So now we have to design full adder module, full adder A, B, C in, some C out. Inputs are A, B, and C in, put some and C out. Okay. I think I have that structure. Okay, we will be requiring two half adders and one OR gate. Whatever carry we have from half adder 1 and half adder 2, we will be ORing that. So one OR gate and two half adder is required. Okay. If you guys have any doubts, I will explain. Okay. X1, C1 and C2. So now we have created the module for uh, half adder. Now we have to include that half adder inside our full adder module. How we are going to do that? We are going to instantiate that inside our full adder. We will call that module name, and we are going to give the module object name we are giving h1, and inside that we are going to give inputs and outputs in the order of what are mentioned here. Okay, so first half adder having inputs a and b. Sum I have taken as x1, then carry I am taking as c1. Then again we need an half adder. I'm calling it as h2. For that, inputs are c in, then x1. Then outputs are s, then c2. Then we need a OR gate for g1. We need output as c out. Inputs are c1 and c2. Okay. I'm using half adder module inside the full adder. Why we need that? Why we are instantiating that module inside another module is while we are designing a larger circuit, we will be requiring submodules. We can't design in one stretch. That will be a lengthier code. So we'll be designing submodules and we will be calling that modules inside our top module. So in last, we have just introduced behavioral modeling. In that we have discussed initial statement and always statement. So I already discussed how initial and always have written. We also discussed clock generator code. Now we are going to discuss procedural assignments. In data flow modeling, we are using continuous assignment. We are using a keyword known as assign, right? We are using assign as is equal to ax or b and assign c equal to a and b. That is continuous assignments, which means that it will execute line by line. Okay. So procedural assignment is different from continuous assignments. There are two type of procedural assignments, blocking and non-blocking. What is the difference? We will discuss. Okay. What is continuous assignment and procedure assignment? I have created a table of their differences. You can read this later. I'm directly going to what is blocking assignments and non-blocking assignments. Blocking assignments are executed in a order they are specified in a sequential block. So we are defining some assignments there. So it will be executed in a order. What order we are specifying that assignments, that will be the order they will get executed. So if you are writing S is equal to X or B and C is equal to A and B, in that order, if you are writing C equal to A and B, that will be executed first. So if I'm writing S is equal to X or B, then that will be executing first. So for uh, differentiating blocking assignments and non-blocking assignments, we will be using blocking assignments as equal sign, yes, equal operator for specifying blocking assignments. But for non-blocking assignments, we will be using less than or equal to, yes. I will be coming there. So we will discuss one blocking assignment example. So I am creating a module blocking assignment example. In that I have taking three registers A, B, and C. So always at bracket star begin. You don't focus that sentence now. I'm just going to explain what is blocking assignments. Okay. C is equal to A and we have written. In that I have taken blocking assignments. How I get to know that it is blocking assignments? So in that it is equal to operator. Okay. Whatever we are statements we are writing, if I am using equal to operator, then that will be a blocking assignments. What is the use of blocking assignments? The use of blocking assignments is that it will be executed sequentially. Whatever order we are given, that will be executed sequentially. Okay. So yesterday, I there are so many system tasks. One of the such system task is $sign display. This is used to display that variables during the simulation runtime. So here I am going to display the value of A, B, and C. In invert comma, we will be defining the string what we are going to display. Percentage B I am representing, or you can use percentage D if you want. That B and D are, B is binary and D is decimal. Okay. So outside that inverted comma, we will be defining that order of first invert percentage B will be representing A value, second percentage B will be representing B value, then third will be representing C. Okay, then I'm giving some value for A and B, and after 5 nanoseconds, I am changing the value to 1. Then again, I'm waiting for 5 nanoseconds, then I'm finishing that simulation. This is also another system task used to terminate that simulation time. Verilog is case sensitive. Okay, yesterday I told, I think. So this is an example of blocking assignments. Any doubts in blocking assignments? This blocking assignment is not a new topic. This is same as whatever we are done in data flow and sequence means gate level, but we are not using any keywords before this assign, or we are not going to use that here. Inside always block or initial block, we can directly write that statements. For behavioral modeling, there are two blocks, initial and always. Inside only that only we will write all that statements. So the next assignment is non-blocking assignments. Non-blocking assignments allow scheduling of assignments without blocking execution of the statement that follow in a sequential block. It means that if we are using A equal to 0 and means A less than or equal to 0 and B less than or equal to 0, at the same instance, both value will be updated. That won't block the execution of next statement in means written inside that sequential block. That's why it's known as non-blocking assignments. We will be using less than or equal to operator for specifying that. Okay, then the execution of non-blocking assignments will be carrying at simulation time equal to 0 only, but the variable will get that value, and there will be a change occur in the there are before discussing this, there are 4 regions. In that, non-blocking assignment region is the active region, passive region, then NBA, and one more region is there. I couldn't recall that. Uh, okay, so this non-blocking assignment will get executed in the non-blocking region, non-blocking uh, assignment region. So all the blocking assignments and procedural assignments, not continuational assignments, all will be executed in active region. That is during the simulation time itself. But non-blocking assignments will be executed after the simulation. That is non-blocking assignment region. Just for our knowledge, and don't worry about that. Okay. So this is an example of non-blocking assignment. Same as I'm naming it as non-blocking assignment example. And I'm taking 3 registers A, B, and C. Here I am written always at positive edge, post edge clock, then begin. I'm using A less than or equal to B and C less than or equal to A. Can anyone tell me if initial value of A is, I think everyone have notepad or notebook with you. Just note down the values of A, B, and C. Here the value of A is 5. Initial value of A is 5. B is 6. C is 10. Then after this execution of this code, what will be the value of A and C? Here, uh, whatever value in B I'm going to give to A, and whatever value in A I'm going to C. Because of this non-blocking assignments, the both sequence will be means assignments will be executed at the same time. But the updation will be taking place after the simulation, which means that uh, I am given the value as A as 5. So the same value will be getting C. It won't be 6. Okay. So after the full execution, A value will be 6, B value will be same 6, and C value will be 5. That is the difference between blocking assignments and non-blocking assignments. Uh, Actually, for every interview, you will be facing the same question. In every interview board, they will ask what is the difference between blocking and non-blocking assignments, and they will give you an example, and they will ask what is the value of this register after the execution. That's a common question. So take care of that. Then we are going to discuss different timing controls. We have three methods of timing controls: delay based, event based, and level sensitive based. Okay, we will first discuss delay based. So delay based is we will define some time duration in the statement so that it will execute that statement or encounter that statement whenever that time is matching. It may be a number or identifier or min type max expression. So we have three types of delay control: regular delay, intra assignment delay, and zero delay. Regular delay is whatever we have explained in all the codes. We are using the regular delay. So this is regular delay. Yesterday, someone asked what is hashtag 10. So that is a regular delay control. Whenever that 10 nanosecond is exceeding, then this statement will execute. So other method is we can use keyword parameter, and we can name the parameter, and we can give the value to that, which means that inside the code we can directly code. If I want to give something some variable 20, instead of 20 I can directly write it as latency. So that is identifier. Okay, other we can directly write some equation with that identifier using I am using latency and delta as two parameters, having the values 20 and 2. So for that delay, I'm giving hashtag latency plus delta. Then the next thing was minimum, typical, and maximum values, which means that this is the minimum delay, this is the maximum delay, and this is the typical value. Whenever uh, this simulation environment encounters 5 nanosecond delay, typically that sequence means statement will execute. If we are finishing the statement means the simulation before 5, hmm, even if it is encountering 4 nanoseconds, it will execute. That is minimum value. It should contain, and we are setting that as a range. Okay. So there are three definition. Uh, with number we can define the delay. With identifiers we can define the delay, and using mean, typical, maximum delay values. Basically, we are not using mean, typical, maximum delay values in our codes normally. We will be using identifiers as well as numbers. Mostly we will go for identifiers. We will be defining some parameters in our code, and directly we will calling that parameters. If some delays in some architecture, delay may be a constant value. If we are not following that delay, it will encounter so many issues. So we will be fixing that value using parameter, and we will be calling that only. Otherwise, while coding, if someone making some mistake, there will be an issue. To avoid that, we are using that. Okay. So the next assignment is intra assignment. Intra assignment is like this. In this, you can see this. So what this means, x and z having initial value 0, 0. Hmm? Both the values will be taking into x and z at time equal to 0 only. But evaluate x plus z at time equal to 0 itself. In the above case, here, if I'm saying y is equal to some x or b, okay. In this case, this will be executed only after 10 nanosecond delay. But in this code, it will be executed at t equal to 0 itself, but updation will be taking place after 5 nanoseconds. How to convert this intra-assignment delay into regular delay? That is written here. So we will be requiring another register. First, we will be adding that values and we will be storing this to a temporary register, and we will be using the same regular delay assignment. After 5 nanoseconds, temporary register value will be assigned to I. So this is the same as working as this. Okay. So the next one is zero delay. Zero delay actually used to eliminate race conditions. I think everybody knows race around condition and all. Okay. But there is an issue with using this zero delay control. It may be actually most of the designers does not recommend this has zero practice. So just for the knowledge, I am going to explain this zero delay control. Just we will be adding hash 0. That's it for zero delay control. Why we are using zero delay control? We can explain that it may get eliminate that race conditions, but we are not recommending this. Okay. So the next one is, first we have discussed delay timed based delay based timing control. Now we are going to discuss event based. Okay, so we have three types of event based timing control: regular event control, named event control, and event or control. We'll be sharing this PPT, so don't worry about this theory. Just I want to explain that whole concepts little, so that you will get to know what is going on in the code. So in regular event control, we will be using at. Later, as I discussed non-blocking and blocking assignment examples, I have mentioned always at. So at that time I said to ignore that line. So we are going to discuss what is that at symbol specify, and inside that bracket what is that star and what is posets and all those things. So in regular event control we will be using at, that is event control. Statement will be executed on change in the signal value or at the positive or negative transition of the signal value. Okay, different statements I have written here: at clock, at posage clock, at negate clock, then at posage clock. What is the difference between all these statements? I will explain one by one. At this, if signal value is changing from 0 to 1 or 1 to 0, this q equal to d will get executed. So this is the condition. At in bracket, whatever signal we are representing, if that signal value is changing, then whatever state writing, that statement will get executed. So what is posage and negates? Positive edge of a clock and negative edge of a clock. When the clock is moving from 0 to 1, or uh, here 0 to 1 or 0 to x or 0 to z, or x to 1 or z to 1. These all are the transitions. which one of the transition is happening, then this q is equal to d execute means statement will get executed. Likewise, in negative edge, if it is moving from 1 to 0 or 1 to x or 1 to z or x to 0 or z to 0, that transition, if clock is having that transition, then q equal to d will get executed. Okay. In this statement, the difference is d will be evaluated immediately, but it will be assigned to q whenever there is a positive edge of a clock. The next thing is named event control. So these are the topics. Actually, that is not basic. This named event and named event door. Event door is we record, but named event we usually don't use. We will use this regular event and event door. Okay, we can declare an event and then trigger and recognize the occurrence of that event. The thing is, event can't hold any data. We will be declaring event with the keyword event only. Event is triggered by that symbol, this arrow mark, and event is triggered by at symbol. Okay, so arrow mark is used to trigger the event, and to recognize that event, we will be using at. I have written an example here so that you will get to know what is that. Okay, here I'm taking an event named as received data. Okay, so whenever there is a positive edge of a clock, this if block will execute. So if last data packet, if inside this if statement I'm writing only one variable, which means that if that value is high, which means that it's equal to 1, it can also represent like this, equal to 1. Okay, instead of that we are simply writing like this. So if last packet is received, that is the meaning of this, then we will trigger that event. For triggering we are using arrow. Okay, so whenever that received data value is changing, then we will be giving our data buffer the data. Okay, the next one is event door control. This is event door control. I have reset signal, then clock signal, and D signal. I'm using in between OR gate. So this is level sensitive. Whenever the value of reset or clock or D changes, then this part will get executed. This is an example of a level sensitive latch with asynchronous reset. Any signal that is depending on clock, that is synchronous, and if it is not depending, that is asynchronous. Here, if I am not using reset in the inside here, then it will be synchronous reset. Whenever clock is changing, at that time only we are checking whether it is high or not, reset is high or not. But if I am adding reset here, which means that even if reset is changing, then this code is executed irrespective of clock is changing or not. Okay, so that is synchronous and synchronous. I guess everyone understood this line. Event OR is used in between of every signal. Okay, so one thing is, if I am designing a large circuit containing 150 input, 150 or 160 inputs. So inside typing, inside this always block, I am typing all these 160 inputs. That is will be an hectic task. Even in between, maybe I will miss some signals. So for that, if I want every signal to be sensitive, so what is sensitive? First I will explain that. Whatever signal we are representing inside this always at bracket, inside this bracket, whatever signal we are representing, that signals are sensitive. Sensitive is whenever the signal value is changing, that always block will get executed. That is sensitive signals. Okay. So in my model, that 150 signals are sensitive. So I need to write 150 signals inside that bracket. So that is not possible. For that, we are using different thing. And another way of writing this or is we can use comma. Instead of or, we can write it as comma. Okay. Same code I have written in different. So for that, we are using this at star, or you can use at bracket inside star. So that's why in this code, I will explain. In this code, I have written star. Whatever inputs I have, that all are sensitive. If any one of that signal is changing, then this always block will get executed. So for event OR gate, we can represent like this using or we can represent it by comma. Or if you want to write all signals as sensitive, then we can use asterisk sign. So now level sensitive. So what is level sensitive and edge sensitive? What is level and edge? Is it clear, right? Any doubts so far? It's important if you are learning Verilog. The thing is, if you are not able to design sequential circuits, then there is no use of learning Verilog. Every design in our practical application require a memory element. Every memory element is a sequential circuit only. Even counters are used in every, most of the circuits there will be a counter. So this part is important. Okay, so next timing control is a level sensitive timing control. Level sensitive timing control, we will be using keyword wait. So I have a count enabled. Whenever that count enable is high, then this statement will get executed. After 20 nanoseconds, count is equal to count plus 1. So it will wait, and we are using keyword wait up to whenever this count enable is high, up to that it will wait. Okay. So for level sensitive timing control, we are using the keyword wait. I think timing controls are clear. Now we will be discussing some topics that is required for designing conditional statements, then loops, multi-way branching. Conditional statements, if else. First I am going to discuss is if else. If statement, then true. That is one type of expression. And second type is we are using if and else. If expression, true statement, else, false statement. Then third type is nested if else if. If statement means expression, true statement, else if expression, true statement true, else we will be defining default statement. This is the way of representing if else statements. Okay, these are the examples for first type. If lock is, what is this represents? Not. If in condition, we are not representing using this. In operators, we will be using this. But if you want to give not in condition, we will be using this. That is bitwise not. This is logical not. The difference is explained in textbook, whatever I shared yesterday. You can see the. So this expression is representing if log value is not 1, which means that if log value is 0, then buffer is equal to data. If enable is high, then out is equal to 1. For type 2, we have if and else part. If count is less than 10, then I am incrementing count value, count is equal to count plus 1. Else I am displaying counting error. So for display, we can display string like this. I already explained what is display function. That is a system task. Okay. Then the third type is nested if else if. If control equal to 0, then this will be executed. Else if control equal to 1, then this will execute, or if else 2, then this will execute, otherwise invalid control. Likewise, you can give conditional statements. Then the next one is multi-way branching. So nesting if else if is large, if we are going for a design of a large circuit. So for that, we are going to use case statements. Shortcut way of writing if else if. So for that, we are going to use case and default. These three keywords will be there in case. Okay. So I have to write case. The same if else if code I have written in case. Our control signal is control. So case control. If control value 2-bit in decimal 0, that is 2 tick D0. So if the value of control is 0, then this will execute. If it is 1, this will execute. If it is 2, this will execute. Default is also keyword that is necessary to write default in case statements to avoid erase around conditions. So default display invalid control. And if we are starting case, we need to end the case. So this is 4 to 1 multiplexer with case statement. So I'm starting with module mux. Then we have only one output. Then we have 4 input, then 2 select line. So I already discussed whatever outputs we have for behavioral modeling, we have to represent it as reg. Okay, then input will be wire. These all are inputs. Then all the inputs are sensitive. That's why we are using star. So in these control signals are these select lines. So this curly bracket is used to concatenation. Okay, S1 is single bit, S0 is single bit. If we are concatenating single bit and single bit, we will get 2-bit. Okay, that's why we are writing 2-bit data here. Okay, so case inside bracket we have to give the condition control signals as S1 and S0. If it is 0, then output will be I0. If it is 1, then I1. If it is 2, then I2, 3, I3. Default we are representing invalid. Then we are started case, that's why we are ending case, then module and module. The next thing is in case statement. Case X, case Z. These are 3 different cases we have. For case statement, we will be comparing all the values 0, 1, X, and Z. What is X and Z? X don't care values and Z is high impedance values. Z. So for case statement, this all value is taken into picture for comparison. But for case Z, treat all the Z values in the case alternative or the case expression as don't care. Z can also represented by question mark in the position. Okay. If it is case X, treat all X and Z values in the case item or the case expression as don't care. So in case Z, Z is treated as don't care. For case X, this X value and Z value will be treated as don't case. You guys don't worry about it. We will be taking only case statements. Just for knowledge, means explain this case X and case Z. So this is an example of how to use case X encoding. So for encoding, there will be a what we say that one have uh, word for it. We will be only looking the position of this one. All other values we will be treating it as don't care. That's why we are don't representing all the what if it is 4-bit, it contain 2 raised to 4 combinations. So that will be a large task. So for uh, avoiding that, we will be using case X. Instead of writing all the combinations, we will be directly writing XXX. So if it is the one position is in the 4th stage, then the next stage is 3. Likewise. Okay. So according to our requirement, we are designing. If it is case statement, we have to write all the possible combination. So for to avoid that task, we are going to case X. So loop, we have while loop, for loop, repeat, forever. While loop, I have already discussed during counter, I guess. Integer, I have this is another data type we can use. Count, then initial begin. I am giving initial value of count as 0. Then if count, while count value is less than 128, I am incrementing the count value, and after that it will get ended. So it will start from 0, it will count up to 127, 128 or 127. 127 will count up to 127 and it will get ended. Okay, a simple example of while loop. Then for loop, the same code I have written in for loop. I think similar syntax is for C++ also, C or C++. Both contain the same syntax. For we will be initializing the value and we will be giving the expression and the updation expression, and we'll be giving the statement. For repeat, same, we will be giving, then we will give the repeat value. How many times this statement need to be executed, that will be representing using repeat. Okay. The next thing is forever. During clocks generation, we have used always in place of forever. So the another method of generating clock is using forever. Forever as 10, clock is equal to negation of clock. So it will negate the clock every 10 nanoseconds. Okay. So I completed the theory part. Now we will be discussing the code, how to design the flip-flops. I think the code is visible. Okay. So the first thing we are going to design is synchronous SR flip-flop. So this is the truth table of SR flip-flop. For 00, no change will be there. Then for 01, same 01, Q and Q bar. Okay. 1010 11. This is prohibited in case of SR. Okay, we will be representing it as don't care. So we'll be starting our module. I think this is okay. So we'll be starting our module. Then we are giving it as name SR underscore flip flop FF. We have inputs S, R, clock, and reset, and output Q and Q bar. Then all the inputs are wire, and Q and Q bar are register. So SR flip flop is edge triggered That's why I'm using positive edge of clock. Whenever we will encounter a positive edge of clock, then this always clock will execute. If it is reset, then Q will be resetted to 0 and Q bar will be resetted to 1. That is their default value. Else, we will be taking case statement. As I already mentioned, this curly bracket is used for concatenation. We are concatenating our control signals S and R. If S value is 0 and R value is 0, Q will be Q, Q bar will be Q bar. There is no change in the output. If S value is 0 and R value is 1, it will be 0, 1. If it is 1, 1, 1, 0, it will be 1, 0. If it is 1, 1, then that is prohibited in SR. So we'll be giving don't care. Then N case, then N and N module. Understood? So if you know that truth table, it is easy to design the SR flip-flop. We don't require the internal structure of this SR flip-flop for that. If we know the internal structure, we can directly go for uh, gate level or data flow. But if we only know that truth table, what happens when if the input is changing, then this is the output. If you know the only we know that data, and this inside that block is black box, so we will go for behavioral modeling. That's why we most of the design will be designed in behavioral model only. Inside that part we don't require only uh, what are the values of output for the particular combination of inputs. That is the only thing we require for designing. Okay, now we are going to explain the test bench, how to write test bench. Likewise, whatever we are written for full adder or half adder module, then SR underscore FF underscore TB, whatever inputs we are written in our code, design code, that will be reg here, and whatever output we have written in our code, that will be wire here. Okay, then I am instantiating our module, design module inside our test bench. Then we are another system task is monitor. For display, we need to write after every variations. Otherwise, if we are only representing one display function after all this, it will show only that what change. But if we are using system monitor, means dollar monitor, then for every change in the clock S, R, Q, and QB reset, it will display in that log file. So in place of using five different five, one, two, three, four, five, six different display functions, we can use one single statement of monitor. Okay. So I'm using monitor. Then I am giving the value for S and R. The first thing you have to do is first we will be keeping both S and R is 0, and we will be giving reset, and uh, we will be giving clock value 0, 0 or 1 according to your wish. Actually, the code is asynchronous or synchronous. Okay. So we need to give clock value as 1, otherwise that reset won't work. So we are giving initial value as S equal to 0, R equal to 0, reset is equal to 1, clock equal to 1. So after 10 nanosecond, we are giving reset 0, and we are giving all the possible combinations 1 0 0 1 1 1 and 0 0. Then we are giving again reset. Then for every 25 nanoseconds, we are negating our clock. This is clock generator. In place of always, you can use forever if you want. Okay. Likewise, we can design the flip-flop, then JK flip-flop, then T flip-flop. Okay, all the thing you can design. Only thing we are requiring is truth table. If you know the truth table, you can directly write the code. Syntax. I will be sharing this, okay, so that you can do with. So first we have given one. So we are giving one, then reset one. Both S and R are zero. So Q will be zero and Q bar will be one. If reset is one, that is the thing we have written in the code. Then after every 25 nanoseconds, that clock is toggling. So that clock period is 50 nanoseconds. Okay. So the next thing is we are giving zero for the entire cycle for reset, and we are giving possible combination of S and R. The next thing is it won't get executed up to this. Whenever they are encountering a positive edge of a clock, that is this. Whenever they are encountering a positive value of edge, that's the thing, the value will change. Up to that, even if S is 1 up to that, there is no change in Q and Q bar. You can only see the change whenever they are encountering a positive edge of clock. So when they are encountering positive value of edge of clock, then they will check what is the condition. Reset is 0, so they will go to the case statement. And what is the value of S and R? S is 1, R is 0. So it will be 0 and 1. Okay. Then next positive edge of clock. At that case, it will check what reset is 0. Then here S is 1, R is 0. So same 1, 0. Then for next clock period, positive edge of clock period, reset is 0, R is 0, and means S is 0, R is 1, then it will be 0 and 1. Accordingly, you have to verify your waveform. Just plotting the waveform is not what we want. You have to also verify whether it is correct or not. This red part is representing the don't care. Okay, verify accordingly. Okay, so we have discussed behavioral modeling, gate level modeling, and data flow modeling. The only left is shift switch level modeling. So I have already discussed that switch level model can't be synthesized. So what is synthesis? Synthesis is whenever we are writing a code, all this code, after we will be doing uh, synthesis. It will be converting this entire code into gate level, which means that uh, we are writing the code in Verilog. So uh, for the designing part, we have written code in textual format. So we need to convert that into graphics, means or block diagrams. For that, we are using synthesis. So synthesis is something uh, that converts the textual into graphics, you can say. Hmm. But whenever we are synthesizing, it need to be assured, means check whether that uh, design is what we are designed. Sometimes there will be design mismatch. There will be some buffers there, then some unwanted blocks will be there. So we need to change according to our uh, design requirement. We need to change the code. That will be uh, most of the processor design and uh, but which as ASIC and FPGA designing these cases is normal. There will be unwanted modules will be there, so we need to change this entire code and we need to verify whether where that particular block is coming. For example, in the case of I already explained, if in the case of if else block, if I am representing if control is 1, we need to execute this. We are not representing what happens if control is 0. In that case, if control is taking place in 0, it will be going to a buffer. So for every signal, if we are taking it as a control or expression signals, we need to provide every possible combinations. If we are not representing every combination, there will be an undeterministic stage. So the system will create an unwanted box and it will store that signal there. So according to our design requirement, we have to change the code accordingly. So for that, we are using synthesis. Every gate level and behavioral and data flow are synthesizable, but switch level modeling is not synthesizable because we are using NMOS, PMOS for dividing. That is the lowest basic element that cannot be further synthesized. Okay. So this is the first thing, switch name. How to instantiate this switch element. Switch name, then instance name, output, then input and control. Okay. So I think everyone knows CMOS inverter. This is PMOS and this is NMOS, and we are connecting that in complementary MOS circuit for inverter or NOT gate. Okay. So I'm starting my module with module, and my module name is my NOT. Then we have input X and output Y. So in the structure, it is not Y. So we will take it as Y only. Okay. Then we have supply high as VDD and ground as this. So we have to represent that as supply 1 and supply 0. For supply 1, that is VDD. For supply 0, that is GND. And we have to use the switches. But the syntax, switch name, instance name, output, input, control. So output is for PMOS, this is the output. For NMOS, this is the output. In basic semiconductor device, we have to know that basics. So output, then for PMOS, input is VDD and control signal is X. For NMOS, output is Y, then input is ground, then control signal is X. Okay. So accordingly, I have written output VDD X for NMOS, Y, ground, X, N module. This is how we create CMOS inverter or NOT gate using switch level modeling. I have just explained how we are designing this switch using switch level modeling so that we can cover all the modeling. If someone is asking, can you explain the code? If that code is in switch level and you are saying, I have not learned this, my sir is not teach me this. So that's why I have explained. If someone is showing you this code, you can now explain. I have explained every modeling now. So that is the basics of Verilog. Now you know how to code in data flow, then gate level, behavioral, then switch level. The test bench will be remain the same. Okay, all the things I already discussed, that will be the same for test bench. Then I have already means also included NAND gate, NOR gate for your reference. Then I have already explained all these things. Okay. Okay. So the next thing I want to discuss how to include. So this is an additional topic. If you want to, you can uh, means uh, this is an optional thing. I have already defined means explained the predefined gates. We have AND gate, NAND gate, OR gate, or NOR gate, XOR gate, XNOR gate. So I want to create my own gate. So I need to create Sangeedh as a gate. So how we can create that? So for that we have a keyword called primitive. Instead of model, we are going to use primitive and that primitive name. And inside, the only thing we can see as a limitation for primitives are we can only represent one output. Okay. So for primitive, we will be defining our output first, then inputs. So output is F, then inputs are X and Y. Then we will be taking a keyword as table. In that, we will be defining our combinations. If X is 0 and Y is 0, then F is 0, then it is 1 0, then it is 1. If it is 0 1, then it is 1. If it is 1 1, it is 0. Then for the keyword table, we are using n table, and for primitive, we are using n primitive. Likewise, you can create your own gate, and you can use that gate. First, you have to use this code, like we have to include here input main code, like this. One second. I want to include this. I want to include this XOR. My XOR, inside this, we need to use my underscore XOR. Then first we need to write the output. Sorry. So first we have to write sum, then comma, then our inputs A and B. So sum will be A and B. A XOR B. Sorry, XOR is the answer. So likewise, you can create your own gate. The limitation is we can only represent it for one output. Okay, then I'm stopping here.